Welcome back to the Learning Studio. You're watching our mathematics series, where we uncover the most powerful concepts shaping science, technology, and artificial intelligence. If this is your first time here, make sure to follow us by clicking the link below. And don't forget, the full playlist is also in the description, so you can catch up on all the episodes in order. Today, we're diving into one of the most fascinating areas of mathematics: complex analysis. At first glance, it's all about imaginary numbers, but as you'll see, this imaginary world is actually one of the most practical tools in modern science and engineering. Let's start with a mystery. For centuries, mathematicians worked with equations like x squared plus 1 equals 0. The problem? No real number could ever solve it. So they invented a new kind of number, I, the square root of minus 1. At first, people laughed at the idea. They called them imaginary numbers, as if they were fake. But what began as a curiosity turned into one of the most powerful inventions in human history. Complex numbers, numbers with both a real and an imaginary part, opened the door to complex analysis, a branch of math that touches everything from signal processing to quantum mechanics. Here are the essentials of complex analysis. Complex numbers. A complex number looks like a plus bi, where a is real and bi is imaginary. Together, they form a point on the complex plane. Functions of a complex variable. Just as we study functions with real inputs and outputs, complex analysis explores functions with complex inputs. Surprisingly, these functions often behave better than real functions. They're smoother, more predictable, and deeply connected to geometry. Contour integration. Instead of just integrating along a line, complex analysis lets us integrate along curves in the complex plane. This powerful tool makes solving difficult real integrals much easier. Residues and poles. These might sound intimidating, but they're simply ways of understanding where complex functions blow up or have special behaviors. They're crucial in physics and engineering, why it matters in technology and science. Now let's talk applications, because this isn't just abstract math. In signal processing, complex numbers are everywhere. Fourier transforms, which break signals into frequencies, rely on complex exponentials. That's how your phone compresses audio, or how images are processed. In control theory, engineers use complex analysis to study stability. Airplanes, robots, and even power grids depend on these methods to make sure systems don't spiral out of control. And in quantum mechanics, the very equations describing particles and waves, Schrödinger's equation, for example, are written in complex numbers. Without complex analysis, we wouldn't be able to describe the microscopic world at all. So complex analysis takes what once seemed imaginary and shows us it's more real than we ever imagined. It's the mathematics that turns abstract symbols into powerful tools for science, technology, and engineering. In our next episode, we'll step into optimization theory, the study of finding the best possible solution, whether in business, engineering, or training neural networks. If complex analysis is about exploring a new dimension of numbers, optimization is about making the smartest choices in a complex world. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode takes us deeper into the mathematical universe, and we're just getting started.